We are now going to look at another way to try to find what the best model is. In other words, how can we select the best variables for our model? This particular way to do this is called, they are called stepwise search algorithms. As you will see, there's actually 3 separate algorithms that are all very similar. And the advantage that these algorithms have are that they are pretty simple to use, they're pretty fast. The disadvantage, though, is that unfortunately they are not as good as finding the best model in comparison to the other methods that we've looked at. So why do we discuss these models and these algorithms if they're not as good? Well, there can be situations where some of the other methods that we've discussed cannot be easily implemented. Maybe perhaps there's not a function R that will automatically do it for you at the very least. And so that's why these provide a way to approach the model selection process that you may not have otherwise. Also, these methods are still prevalently used or widely used. You may need to, let's say, read a paper or talk to another individual who implements these methods, and so it's very useful to understand what these methods are and how to use them. So there are essentially 3 different ways to implement stepwise search algorithms. We're going to focus on the forward way, and then we'll talk about a backward and stepwise way, or a both way, some people will call it. So to do forward selection, what we do is follows. We compute the information criteria, so we're still using like the AIC or the BIC for a model with no explanatory variables at all. So maybe just simply, if we're talking about logistic regression, we have this particular model. Then we compute the information criteria for all possible one explanatory variable models. Let's say that we have x1, x2, and x3 as our explanatory variables of interest. So we look at a model with just x1, look at a model with just x2, and look at a model with just x3 in it. And for each of them, maybe we calculate AIC if that's our information criteria. Now the model that has the lowest AIC becomes what we say is our best model, or our current best model. Let's say that the x2 model is the lowest AIC. Then, step 3, we start with this model that has this x2 in it. And we look at models that have x1 and x2, x2 and x3 in it. And each time we calculate our information criteria, maybe AIC. And we look to see if any of those models reduce our information criteria even more. If you find one, maybe it's x2 and x3, that becomes your new best model. If none of those do, then you stop your algorithm and just work with the model that has only x2 in it. And so we essentially continue adding. We're moving forward in terms of adding variables to our model. That's the forward selection procedure. We use the AIC to help choose between the models. Now, to do the backward selection procedure, what we do is we start with a model with all our variables in it. Let's say x1, x2, and x3. We calculate then the corresponding information criteria, maybe AIC. Then we remove one variable at a time and look at those corresponding models. So x1 and x2, x2 and x3, x1 and x3. For each of these models, we calculate the information criteria, maybe AIC. The model that has the lowest AIC, that is less than what the model was for x1, x2, becomes our next best model. If, however, none of these 2 variable models have a lower AIC, we stop with this as our best overall model. So notice how we're going in a backward manner. We start with a large model and then slowly remove one variable at a time. Now, alternating stepwise selection, or some people just simply call it stepwise, some people say it's both, basically combines forward and backward. Simply you do a forward step, then you do a backward step, then you do a forward step, and then you do a backward step. Now you might be wondering, well, how can you do that? Well, as you're adding variables into your model, what can happen is that sometimes a variable that was judged, let's say, important to include early on can now then be judged later on not important and be removed, depending upon, of course, what the AIC or the BIC or whatever value, whatever information criteria you're using. Okay, so let's take a look at how we can implement this in R. We're going to go back to the place kicking data example one more time. And what we need to do first is estimate a model using GLM that has no variables in it. So the way I do that is say my response good tilde, and I put a 1 there, and that basically just says, okay, just estimate a model that has just beta 0. Then we estimate a model that is, let's say, the largest of what we're going to examine. So we say good tilde, and then with the period there that says include the rest of the variables that are in my data frame. Next, the function that does the forward selection is called step. This is in the default installation of R. With the step function, I say object equal, this is my beginning point, empty.mod. So it's the model right here. Then I use a scope argument that basically says how far do I want to go in terms of what the largest model it could be. And the way I can specify that is use list upper equal, then there's my full model. Direction equal forward, k equal the log of the number of rows of place kick. What this is going to give me is simply the log of the sample size. So n row says number of rows of my data frame place kick. Trace equal true. Well, you don't need to do that. I do it here to trace the steps of forward selection so we can see how the process works. So we start as follows. I start with a model that has no variables in it. Its AIC is 1020.69. And then what R does, it looks at, well, let's look at a model with just distance in it. Let's look at a model with just PAT in it, and so on. And we can see in comparison to where we started in terms of the AIC, I'm sorry, let me back up a second here. Notice it says AIC. This is actually BIC. This is actually a problem with the step function, because since I'm specifying my k to be the number of row log of n essentially, I am actually using BIC, but R doesn't have a way to know that, so it just simply calls it AIC. So, excuse me, this is actually BIC being used. Okay, so BIC was 1020.69, and we can see that 3 of these variables ends up reducing the BIC value compared to where it was before. The variable that reduces it the most is distance. So now my model of interest becomes the logit of pi is equal to beta 0 plus beta 1 times distance. Here's that BIC. Now let's look at what happens if I add PAT to the model. What happens if I add change to the model? What if I add wind to the model? And only the PAT variable ends up reducing the BIC even further, reduces it to 784.20. So now my best model has has distance and PAT in it. Here's where it's stated. I look to see if I can add any more variables to the model. And in the end, no variable reduces my BIC any further from what it was. So then the algorithm stops. If you want to see a summary of the corresponding algorithm, the ANOVA function actually does that. We can see the ordering that the variables were actually entered into the model. Okay. Well, what if instead I would have used the AIC itself? And so the code is exactly the same, but I put k equal 2 there instead. And you can look through the process on your own. Eventually we get to the point of seeing what variables were added. And we have distance, PAT, change, and wind. Remember what we talked about before is that Using the BIC, you'll tend to have smaller models than what you would have with AIC, and that does hold true here. Also notice how this AIC picked essentially the same model as what we had previously when using all subsets regression. That is not necessarily guaranteed to happen. Now you might be wondering, well, why? Well, the reason being is because we're looking at a lot smaller set of possible models versus the, I think it was the 256 or 2 to the 8 power different models that we were looking at for all subsets. Okay, some final comments here. On your own, investigate both backward and the stepwise selection process using the both argument value for the the direction. Now, the corrected AIC cannot be implemented with the step function, but in the end, you should think about, well, why would we expect to have essentially the same results as what we got with the AIC? Simply, sample size is really large relative to the number of explanatory variables. If you want to, you could actually implement this approach by hand by simply using the AIC function, just simply programming in the model fitting for each of the models. You could also include interactions in the process as well, but you need to make sure to be able to include then the corresponding or respect the principle of marginality, meaning that if you have the x1, x2 interaction in your model, you need to also have the x1 and x2 main effects in the model. Okay, so this gives an introduction to stepwise selection.